Okay, welcome to the next lecture, which corresponds to section 5.6 in the book on concurrency. We're going to consider how to add a concurrency operator, par, to the language. Now we already had or, and now we're going to have par. So if we look at the syntax, I guess I should I can add in over here also the or. So we had S1 or S2, and now we're getting S1 par S2 as a new kind of statement in the statement syntax. So the OR operator added non-determinism by providing a kind of a branching point in a computation. Like if you saw something that looked like this, then you could say, okay, and that's the same as this. So from here, you could say, okay, continue computing with S1. And you can see S2 is thrown away, essentially. S2 is not continued. In the other case, you say S1 or S2, and then you continue with S2. So when you're computing and you run into an OR construct, you either apply the first roll or the second roll, and then you continue from there. Now, the idea of the par operator is to interleave the evaluation of the statements from S1 and S2. So this can also introduce non-determinism, as we're going to see in a minute. This is what makes concurrent programming so difficult. So here's the rules. The rules are maybe the best way to just see how this par operator is added to the language. So there's two rules that say this rule and this rule both start with S1 and say, okay, if you want to compute this par, choose S1 using the current state S and continue and evaluate it one step using the big step semantics for statements. Now, there's two cases what that's going to give you. It's either going to give you something like this, which is a new statement, S1 prime, and a new state, S prime, or it's just going to return a state if there's nothing else to do. And so these two rules capture the idea that, okay, you can evaluate S1 first. But when the result down here, now let me see if I can erase these without getting rid of everything. Oh yeah, on this I'm free. But what you can see down here is that in this case, anyway, when S1 does not completely evaluate, in other words, it's not the second roll where it evaluates to state, but it turns into a new program and a new state, then you go back and you evaluate S1 par S2. So you continue the parallel evaluation of S1 and S2. Now you have the same thing down with the next two rules, is that you could choose S2 to start with in the current state. So you do that and you either get an S2 prime, in which case you do this more complex thing. You evaluate S1 in parallel with S2 prime, the state you got to up there, in the new state S prime. Or if S2 evaluated to a state, there was nothing left to do, then you just go now and evaluate S1 in S prime, in the state that you got from evaluating S2. So these are the four rules for par. Now, it turns out that really, okay, yeah, parallel operator is a great thing, but kind of hard to use without some kind of mutual exclusion or semaphore operator. And I spent far too much time thinking about how I might give you a simple example of that and realize really it's going to require a pretty significant modification of states, or it's going to require a fairly significant modification of what these arrow operators look like. Probably the main thing is we need declarations. So we haven't got there yet. That's in the next section. So these rules look a little bit like these two rules, or all four of them, but they come in pairs, look like the semicolon rules, except that the semicolon rules, remember, are enforcing that if you got an S1 semicolon S2, no matter what, you're trying to evaluate S1 semicolon S2, or there's two cases. One is that you start evaluating S1 and you don't complete. You end up with this more complicated thing. Or you evaluate S1 and you end up with a single state. Now, in this case, in the more complex case, you take that and you put that as the first element together with paired with the original S2, and you continue in the state S prime. Similarly, down here, you continue, we have to finish S2 now because the semicolon operator is a sequencing operator. So we have to evaluate S1 and S2 completely. And it's the same thing for the par operator. We have to evaluate both of them. So let's see, where did I lost an S? There it is. I don't know. Okay. Now, here is the rule for, just to remind you, because we're going to need it in the section just below, the rule for evaluating an assignment is right here. And it says if you have an assignment, x colon equals A, it evaluates to a new state, and remember this notation here is the function update notation. It's S. Remember that states, S is in states, and states are partial functions from variables to ints. So and this notation here, the S with X mapping to V, is a new function that behaves just like S, except on input X, it maps to V. So when does this rule apply? This rule applies only if you really have the arithmetic expression A getting mapped over here. You have to use the the big step semantics for arithmetic expressions. And so X gets the value of an arithmetic expression. You evaluate the arithmetic expression, get back some value V. And now you use this V to update S on input X. Now, I think maybe in thinking about these things, I ran across an interesting kind of weird case where the assignment rule can apply. But I'll tell you, it's basically if there's an expression, if there's a variable in A that does not, if there's a variable in A that is undefined, then this will never reach a value. I'll talk about it later. I wrote down the case more specifically down below. Okay, so now let's do what everyone likes the most, an example. So if we start here, and here's a program. We've got S1 and S2 in some state S, and what does this evaluate to? Well, you got to go up and look at the par rules, and we say, okay, look, if you consider this x gets a value of 0, that case, what you're going to get is a state. That's going to evaluate to a state. So that's going to be a rule, like if we do S1 rule, that's going to be this rule. So par 2 SSS. So we could apply par 2 SSS. Let's apply that. So we get to, the rule says, evaluate this x gets the value of 0. And what that says, is to take your s and update it. So this evaluates to S2, which is x gets the value of 1, semicolon, x gets the value of x plus 2. Evaluate this in the state S, where x evaluates to the value of 0. And now, I mean, we don't have any choice. We just have to use the standard semicolon operators. And so now we get x colon equals 1. I'm sorry. We evaluate that one. And so now we get x colon equals 2. And we're evaluating this now in the state where x got updated to 0, and now that state, x gets updated to 1. But this, of course, is just the state S where x gets the value of 1. And now that goes to S, where x gets the value of 1, updated to be that x gets the value of 3, which is just equal to S, where x is equal to, gets the value of 3. All right, so that's one possibility. Now the other one is a little bit, there's maybe I guess I should let's look at the other one, because the other one's kind of interesting. So the other one is the rule where we apply S2, so we apply this rule that has S2 being incompletely evaluated. And so now we get to still keep S1 around. So maybe I can just keep going out to the side. I don't know. Is there duplicate? No. So let's try it down here. We'll say, okay, x gets the value of 0, par, x gets the value of 1, followed by x gets the value of x plus 2 in state S. And now we're going to apply, this was the par 2 SSS rule that we applied first. And now what we're going to do is we're going to apply, let me just make this is a new section, a new evaluation. Now we're going to apply the par 3 as SS rule. And so here's my S1, here's my S2, and what that basically says, the par 3 rule says, okay, evaluate S2, and then when you get this new thing, plug that in together here and the new state there. So what are we going to get? We're going to get that evaluates to, we still have this. And now what we have is x gets the value of x plus 2 in the state S, where x has the value 1. Now, here's where some non-determinism comes in. In the first case, we got x evaluating to 3. In this case now, we can do one of two things. We can either do the par 4 SSS rule and evaluate this first, which is going to evaluate to a store or a state, or we could evaluate this first. And it turns out it matters which one we do first. Because right now, in the current state that we're in, x has the value 1. Now, if I do set x to 0 and then finally set x to x plus 2, I get back to x is 2. But if I start in the state that has x has the value 1, and then I do this one, and then I get the state where x has the value 3, but when I evaluate the x 0, I get back 0. So there's kind of two different evaluation paths we could take here. So let's try the first one first, I guess. That's par 2 SSS, and that would take us to x gets the value of x plus 2 in the state S, where x gets the value of 1. And now that state gets updated to say that x has the value 0. And so, but that's just the same as, that's just the same as this thing is equal to x gets the value of x plus 2 in the state S, where x, whoa, what's it doing? X gets the value 0. And so then that one evaluates just using the assignment thing to the state S, where x gets the value of 0 plus 2 is 2. Now, at this point, though, we had another choice up here. At this point here, we had another choice. We could have applied par 4 SSS. So let me start. Here, and I could say, okay, we can evaluate x gets the value of 0, par, x gets the value of x plus 2, comma, in the state S, where x gets the value of 1. We could evaluate that using the par, and this is the par 4 SSS rule, which I'll show you. Par 4 SSS rule is here. It says that go ahead and evaluate S2 first, and then evaluate S1. So we're going to evaluate down here, we're going to evaluate S2 first. space. Okay, so I've got the par 4 rule will evaluate to x gets the value of 0 in the state where as x is updated to 1, that state gets updated so that x is updated to 3. But that's just equal, and that, well, I mean, so now we can either evaluate x0, or we can say, we can simplify the state. We could say x colon equals 0, comma, s, where x goes to 3, and that evaluates to the state where x goes to 3, gets updated so that x goes to 0, but that's just the same thing as s, where x goes to 0. Okay, so what we have now is we've had 3 different ways of evaluating this thing, and in one of them, the answer that we got was whatever the starting state was with x having the value 3. We had another evaluation path that led to a state where x has the value 2, and we had another state where, evaluation path where x ends up with the value 0. So those are this is clearly non-determinism. In fact, you could say that, you could say that the program x gets the value of 0, par, x gets the value of 1, semicolon, x gets the value of x plus 2, is similar to x gets the value of 0, or gets the value of 2, or x gets a value of 3. These two programs